Hello everyone. Our team is dedicated to develop a respiration monitoring device using ultrasound, and my work focuses on streamlining ultrasound signal processing and developing deep learning models for airflow quantification. Sedated patients can experience respiratory complications even with the use of current best monitoring practices. This is important because obstruction can happen seconds after sedatives are administered, and death can follow after only a few minutes. These two children and a man died due to sedative drug administration for dental procedures and routine colonoscopy. Current devices measure downstream effect of blocked airflow resulting in delayed notification. There is an urgent need for a respiratory monitor that provides real-time and quantitative feedback about the respiratory changes which affect airflow. We propose to use ultrasound signaling to measure airflow in order to predict real-time respiratory deterioration, which will empower healthcare workers to intervene proactively to avert respiratory failure. Here's an example showing an extreme breathing event during sedation. When the sedative is given, the patient stops breathing. Post-wave Doppler signals shows real-time airflow changes during the event, as you can see in the first row in the multiplot. Current monitors in use such as pulse oximetry and Untitled CO2 show delayed detection of this respiratory event. In order to provide more information about the respiratory changes, we want to quantify the respiratory flow from ultrasound signals. In order to do that, we collect ultrasound data and the spirometry flow from the healthy volunteers simultaneously. Spirometer is an FDA-approved device to measure respiratory flow medically, and we use this data as a gold standard of airflow in our model training later. We collected two types of ultrasound data: the BMO video of the neck looking at the directional motion during respiration, as shown in the bottom left figure, and the pulse-wave Doppler data collected around the cricothyroid membrane as indicated by the orange cursor, as shown in the bottom right figure. The top right figure shows corresponding respiratory flow measured by spirometer. Green blocks indicate inspiration and the yellow blocks indicate expiration. We use these two types of ultrasound data in the flow estimation models. LSTM is a recurrent neural network-based architecture that is capable of learning long-term dependencies and widely used in natural language processing and time series modeling. We adopt and modified based on the bidirectional LSTM for flow estimation model. We compare the performance of the LSTM-based model to the baseline regression model such as linear regression and the random forest regression model. We also compare the performance of using different combinations of ultrasound data as input. Here's a diagram of the model we used. Here we show the mean error of the different models and the input of ultrasound combinations. The smaller the error, the better the model here. Overall, the LSTM-based model outperforms the linear regression and the random forest regression models. The model using both beam mode and Doppler ultrasound signals outperformed the model using single data source, as indicated by the arrows. Here we show, for use in healthcare field, it's important to know the uncertainty and the confidence of the model prediction. Thus, we decided to adjust the model so we can get that information from the model as well. We updated the model so it outputs a distribution instead of a single value with negative log likelihood loss function and exponential activation function. The orange is the ground truth parameter flow, and the blue are the new predictions with standard deviations shows with the arrow bar. In general, the model shows similar performance in terms of the mean error as before, but it gives us more helpful information about the flow estimation. In the future, we will improve our model efficiency and the reliability, and our team also works on making the ultrasound probe into a wearable device. Thank you.